Good afternoon, everyone. I'm Yue Ning. I'm a PhD student from Computer Science Department of Virginia Tech. I will be introducing our work on modeling precursors for event forecasting with nested multi-instance learning. This work is done with my advisor, Dr. Naren Ramakrishnan, and Dr. Huzefa Ranvala from George Mason University. And Sadapan Masia is also a PhD student in our group. So I will first introduce the problem we want to solve, and I will also talk about the background. Then I will move on to the proposed model and how we use the model to discover precursors in our problem. At last, I will show the experimental evaluation for the model and other state-of-art methods. So event forecasting, such as civil unrest movements, disease outbreaks, and elections is an important and challenging problem. From the perspective of human analysis and policymakers, forecasting algorithms must not only make accurate predictions, but also need to provide supporting evidence. In our work, we present a framework that helps to identify the causes related to the event of interest. Specifically, we want to identify the days of importance before an event, and also filter the key documents by providing a ranked list. In this paper, we focus on a specific domain in protest events. The identified key documents are referred to as precursors here. So, what are precursors like? Here, I'm going to show you an example. We find out within 10 days before a protest event, there are multiple events, news reports determined as highly probable leading indicators of the event. Most significant societal events are a consequence of several factors and their relationships between each other. In this example, the leading precursors discovered by our model were articles commenting on standards of living in Argentina and rising poverty levels. The international court delivers a verdict on the debt crisis in Argentina. All these factors led up to the final protest involving the general population across the country, demanding better work opportunities. So in this example, the event we predict is a protest. And we detect several news articles before the event as precursors. So I will introduce a little bit background of multi-instance learning. In supervised learning, each training example is assigned with a label. This label can be discrete or real-valued label. In multi-instance learning, the labels are only assigned to bags of instances. In a binary case, a bag is labeled as positive if at least one instance in the bag is positive. And the bag is labeled as negative if all the instances in the bag are negative. So there are no labels associated with the individual instances. The goal of multi-instance learning is to classify unseen bags of all instances based on the labeled bags as training data sets. So multi-instance learning is proposed as a variation of supervised learning for problems with incomplete knowledge about labels of training examples. So we formulate a nested structure for multi-instance learning that works for our problem. Given a collection of news articles, or you can also use other data sources. So the objective of our study is to develop a machine learning approach to forecast the occurrence of events of interest in the near future. Specifically, we focus on forecasting protest or civil unrest movements in Latin America from a daily collection of published news articles. Here, the prediction labels are binary, and we label event as 1 and no event as 0. And in the nested multi-instance learning structure, each instance news article is each news article is an instance. And we group the news articles for a day to be a bag. And a sequential collection of bags, we call it a super bag. So notice that we only have labels for the super bag, which is indicating there's event happened after the multiple days of documents. So we estimate the probabilities for each instance and each day. Here I'm going to talk about the precursors in the framework. The precursors are defined as an ordered subset of news articles with high probabilities. So we group the news articles published in a day at the first level, like this. And then the collection of individual days at the second level. So a label Y is associated with the second level. And it denotes that whether a protest event happened in the subsequent K days. So here K is in lead time. So positive superbags should have higher probabilities, which means they are more relevant to the event. Negative superbags are assumed to have lower probabilities. Ideally, we want to forecast the occurrence of an event with a longer lead time. So I will first introduce some basic definitions first. We estimate the probability of an instance by a sigmoid function, which indicates how likely it is related to a target event. Here, x of ij is a news article vector in day I, and w is a model parameter we want to optimize. Then the probability for a day is modeled as the average of all the probability estimates of instance on that day. Here, x of I is the matrix of all the documents representations on that day. And the probability of a superbag, which is the second level, being positive is modeled as the average across all the days within the superbag. Now, the objective for the two-level multi-instance learning problem is defined as a combination of several components. So the first component is the empirical loss at the superbag level, which is here is defined as a negative log likelihood function because we have the label for the superbag. And the second component is the crossbag loss, which is defined as a function of j of xi and xi minus 1, because two consecutive days are assumed to have similar probability. We make assumptions that it is a gradual progression for event development. So that's why we define the j function to be probability of day I minus probability of day I minus 1 and the square loss. So another component is on the document level. Because we don't have the labels for the documents, so we have unsupervised loss here, and we use a hinge loss function for the unsupervised hinge loss function for the documents. And we also have a regularization for the model parameter W. For this objective function, we can apply a simple SGD algorithm and to solve the objective with respect to the model parameter W. So the crossbag loss in the above equation does not allow a sudden changes in the day level probability caused due to the newer event happening on the current day. So in this case, we design a variant version of the AML model. We update the crossbag cost with a pairwise cosine similarity of documents on day I and the day before it. So this model, we call it AML delta. Here, delta is the cosine similarity between documents on 2 consecutive days. Also, we also want to explore the difference, the characteristics across days. So in the basic ML model, there's only one single weight vector for all the documents in a superbag. So to model the sequential features of the documents published across different days, we extend this formulation by learning individual weight vectors for each of the history day. Here, omega is the vector of the weights from W1 to WT, and W is a weight vector for each day. So with all these objective functions, we can train the model on our data sets, and we identify the news article as precursors based on their estimated probabilities. For instance, each news article has an estimated probability, and each day has an average probability. So for the event we are going to predict, we select the documents with high probabilities, and then we determine them as precursors, and then we order them by time to form a precursor line. So I'm going to talk about the experiment evaluation. So we evaluate our model on a real-world data set, which is news documents collected from 2012 to 2014 from 3 countries in Latin America. For Argentina and Mexico, the news articles were primarily in Spanish. And for Brazil, the news articles were primarily in Portuguese. And in order to evaluate the performance of the prediction, we use accuracy and F1 score to see how the prediction, how the model predicts. And also, because we don't have the ground truth for the precursors, so we evaluate the precursor discovery by a quantitative analysis and also some case studies. So here, there are many state-of-the-art methods for prediction. The first model we implemented is a GEICF model. This model is published in KDD 2014, and it optimized cost function, which parameterized the whole part relationship between groups and instances, and push similar items across different groups to have similar labels. And the second baseline model, state-of-the-art model is relaxed MI model, which is published in ICCV 2015. This model is designed for image detections, object detections in images. So this model provides a probabilistic estimate for a given document within a bag to be positive or negative. It has a flat bag structure, and it estimates the probability of a bag using a noise OR function. So we modified the relaxed MI model to use by using an average function for estimating the probability of a bag. So this model is I would call it a flat bag version for compared to our model. And we also use MI-SVM. This model just extends the notion of margin from individual patterns to bags. So we also use the standard SVM, which is for classification. So from this table we show the overall accuracy and F1 score for 3 different countries. And within the blue box, we show the proposed model are performing among the best. And for Argentina, in terms of F1 score, we have 8.3% increase. And for Brazil, we have about 7.6% increase in F1. And for Mexico, we have about 5.7% lift. So besides the overall evaluation of the forecasting predictive performance, we also want to know how early the proposed model can predict. So in this table, we show the proposed method compared to relaxed MI model with different lead times and history days to remind you that lead time is how early can we predict. History is the days of documents we want to use. So we observe that with larger lead time, the proposed model does not necessarily lose forecasting accuracy, because sometimes even better. This can be explained by the fact that several times protests are planned a few days in advance. Besides the predictive performance, I will show another part of evaluation, which is for the precursors. As I mentioned, we don't have the ground truth precursors. I will show a case study first. So this figure shows a storyline of a continuous protest event in Mexico regarding the infamous case of 43 missing students. This resulting outrage triggered the constant protests, which were identified by our proposed model. And also this event turned violent, leading up to the burning of the congressional offices. So this is a manual analysis for this for the event for the protest event. While we cannot do the manual analysis for all the events in the dataset. So in the next 2 slides, I show some quantitative analysis of the precursor mining. So we fit the distribution of relative cosine similarity and entity hit for all the documents in the history days, which is shown in the gray line. And the precursor documents are shown in the blue lines for 2 countries here. These distribution figures demonstrate that the proposed model assign higher probability to the news articles with higher semantic similarity to the protest events. So this result shows the strength of a proposed model in identifying the precursor articles. Also, in order to evaluate show that the instances the proposed model estimates the instances in the positive bags are assigned higher probability compared to the instances in the negative superbags. Here, the green bars are for the positive superbags, and the purple bars are for the negative superbags. And we show the results for Argentina and Mexico. So I'm going to conclude the proposed model. In summary, we formulate the event forecasting and precursor mining for multiple cities in a country as multiple instance learning problem with a nested structure. So by estimating the prediction score for each instance in the history data, we automatically detect significant precursors for different events. We explore different penalty functions and regularizations where we employ temporal information in the dataset and the assumption that most events of interest are follow-up reports of other events that happened before. And most planned events are developing over time. So we also extend the nested MIL formulation for general purpose multi-class classification. But I didn't show the results here, and if you're interested, you can read the paper. And to determine the necessary attributes of the events in terms of their underlying population here. So the multi-class classification is for the event populations. So we also evaluate the proposed methods using the news article in the real world in 3 countries in Latin America. That's basically what I'm going to talk.
Okay, let's thank the speaker. Okay, your question?
Thank you for the great talk. I had a question around, did you use any pre-trained models for the topic discovery? And if not, how were you basically doing topic discovery amongst the documents that you used?
Topic discovery, what you
related, so the news articles that you were reading, right?
Yes.
How did you figure out that they were connected, or what were the ways that you used to identify the the topics that they're talking about so that they can be used for causal discovery?
We basically collect all the news articles published in the same city that a few days before the protest event. We are not filtering like for a specific topic. So the news article in the superbag are not necessarily related to the protest.
So then how do you like prevent, for example, like there could be things about sports and weather and all these things. So how do you like, prevent noise from creeping into your analysis?
Yeah, so in that case, the model are supposed to assign lower probability for that for the news article because they are not signals for the events you are interested.
So what's like so basically like what is it that's like that you're using to like determine what is more likely to be a signal and what is more likely to be just noise? What's like the method, like what's like the underlying sort of model that you're using for that?
So the model is designed for detecting the data, like detecting the news articles that is more related to event. That's how the model works for.
Right. So do you have like any sort of like text processing going on?
We did a basic filtering for the news articles because we cannot have all the news articles from sports, weathers. So we have a basic set of keywords to fill the news articles first, and then we train the model. Thank you.
Any other question? Yeah.
So what was the lead time for the?
Yeah, thank you. So lead time is like if I'm going to predict tomorrow, if there's going to have some events. So lead time is 1.
No, I would like to know for your experiment, what was the lead time?
Oh, I tried lead time from 1 to 5 with like, because for each value, like lead time 1, history 5, we train a model.
Okay.
Yeah, basically if we use 5 different values for lead time, we have 5 models.
All right, thank you.
Yeah.
Any other question? So you had in the objective function, you had a term for the bags as well as for the hinge loss for the single instances. What was the rationale for that?
Because we try to maximize the distance between the instance in the positive superbags and instance in the negative superbags. But we don't have the, we just manually set a threshold for the, like, the positive, the estimates probability for the positive instance should be at least 0.5, like the distance between the difference of the probabilities from the positive instance and negative instance should be at least larger than 0.5. So there is a hinge loss function for that.
At the instance level.
Yeah.
No other questions? Okay, let's thank the speaker again.
Thank you.